Much like introducing hydrodynamics analytically in an hour and a half, I have been tasked with introducing numerical hydrodynamics in an hour and a half, which is also a pretty daunting job. So I'm going to preface this by saying that I'm not even going to attempt to cover everything. There are many methods for numerically integrating the equations of hydrodynamics, and I'm just going to focus on a couple of them. But be aware that this is a vast field. The field of computational fluid dynamics is its own group at the APS meeting. So this is by no means an attempt to cover everything, but I think some of the things that are most relevant for astrophysical flows, I'm going to try to get to. So I'm going to start by showing you again these equations, which you've seen plenty of times in the last lecture. So these are the equations of hydrodynamics. And here I'm ignoring all source terms. So no viscosity, no gravity, no heating or cooling, right? And so in this form, you can see very nicely that these are conservative equations. And so as this form shows you, the flux of each of these quantities, density, momentum, and total energy is just equal to the integrated time average of those quantities. And so this is the fundamental piece that we're going to take advantage of in developing these numerical methods is we're going to try to retain the conservative character of these equations. And so I'm going to focus on methods that are explicitly conservative for integrating the hydro equations. And that's one of the things that has dictated my choices in presenting this material. All right, so for completeness, these are a few additional equations that I thought I should define before I go on, because everybody has their own notation for everything. And so I'm going to try really hard to stick to all of these variables throughout the course of the lecture, but there may be cases where I slip up or change something. So as Sasha was saying, if at any point there's anything that's confusing, please just ask. I'd rather you just say, what is that variable? You haven't defined it, than me go on talking about an equation that you can't process. So we've got total energy, which is defined as the sum of the pressure term and the kinetic energy, 1/2 rho u squared. The equation of state, which closes our system of equations, right? And here you can describe that as either rho RT or in terms of the internal energy, rho E gamma minus 1, where gamma is the adiabatic index. That's the ratio of specific heats. And then the sound speed, A, we can define as a function of the pressure and the density and the adiabatic index. Okay, so generally speaking, it is going to be very difficult to find analytic solutions to these equations. They are a coupled set of partial differential equations. There are specific cases where you can find analytic solutions, but they typically involve making very restrictive assumptions, so things like spherical symmetry, et cetera. And so that means that the most common way to approach solving these equations is numerically. And that's going to be the focus of the rest of these lectures. This lecture is what are these numerical techniques that we can use. So here's a brief outline of what I'm planning to cover. First, a couple of different ways of numerically discretizing these equations. And so the two most common techniques, I think, that are used in astrophysics are either sort of Lagrangian-based methods, so following the fluid, and typically that's done as a sort of series of particles, either in an SPH formalism or, there are these sort of meshless finite mass formalisms now. Or in a mesh-based form, so finite difference approximations, finite volume approximations. I'm going to spend more time by far on finite volume because this has sort of traditionally been the best method for capturing shocks, and those are an important feature as we've already talked about in many astrophysical flows. Finite volume methods also couple really nicely to MHD, so that's made them very popular in these if you want to study MHD turbulence or accretion disks, et cetera. And so we're going to spend most of the time talking about finite volume methods. And there are a few key features that go into that. And we're going to spend a lot of time on the Riemann problem. So that's gonna take us through to the end of the lecture. So, as I said, the sort of two main ways that we can think about the fluid, as you've seen from the equations before, are in a Lagrangian sense, where we think of actually moving with the fluid elements and conserving their properties, or an Eulerian sense, where we think of being fixed in a spatial element, and the fluid flow is moving through that element, and the properties are conserved. And so this has led to the two main ways of discretizing these equations in hydrodynamics. The particle-based methods, so SPH, became very popular. It was actually developed later. It was developed in the late 70s, as I'll mention. But SPH has some really nice properties that make it easy to, numerically solve these equations. And there are some sort of more modern forms of SPH. I'm not going to spend very much time talking about them, but you may have heard of, for example, meshless finite mass. This is something that, say, the Gizmo code uses. Or grid-based, and I think there are far more grid-based methods out there, because grid-based techniques have been with us for a long time. I mean, they've been developed since the 1950s, and there are a lot of different ways to apply that formalism. And so, some examples of codes you might have heard of. Zeus is a finite difference code. There are lots of finite volume codes out there. AMR, adaptive mesh refinement, is just a way of using a grid-based code, but also taking advantage of some of the sort of order of magnitude scale problems that SPH is better at dealing with. So I'm going to start by briefly talking about smooth particle hydrodynamics, but I'm not going to spend too much time on it. So, if you have more questions, then that's something that we can address after the lecture. But essentially, SPH just says that we're going to represent the fluid as a collection of particles, and each of those particles has some fundamental hydrodynamic quantities. So, for example, mass. That particle has a momentum, and it has pressure or internal energy or temperature. These things are all related. And in order to evolve this system of particles forward in time, you just use the equation of motion. And so then you can, use additional equations to modify the hydrodynamic properties if you have source or sink terms for the energy, for example. And then you obtain the observables, so things like density and velocity and pressure, through a local averaging process. So what does that local averaging process look like? Basically, if you have a field, we'll call it f of r, you can define a smoothed version of that field, f of s, by convolving it with a kernel, which here I've defined as W of R. And so R is the position of the particle. H is what we call the smoothing length of the kernel. And this kernel, I'm not going to actually put up a specific version of one, but for example, a Gaussian, a 3D Gaussian would be an example of one of these kernels, has some specific properties. One is that it has to be normalized to unity and approximate a Dirac delta as H goes to 0. And then it needs to be symmetric and differentiable at least twice. So within that set of parameter space, you can define actually many different kernels, and people have used many different kernels in SPH codes. One of the things that is nice about this is that this smoothing length H, it can be variable in space. It doesn't have to be a fixed size. And what that means is that then you can accommodate different, if your particles are spaced far apart, you can have a larger smoothing length, for example, than if they're spaced together. And this is one of the things that makes SPH a really nice adaptive scheme for hydro. So how does this actually work in practice? Well, let's say now that we know what the field is at this set of positions, R, and we assume that each of these points has an associated mass, And with that mass, we have a density, so this volume element, delta R, is just going as the mass over the density. Then that means we can rewrite that integral as a sum that looks like this. So now we have SS, the smoothed field is equal to the sum over all of the particles J, where, this sum is just that same field times the kernel with this factor mj over rho up front. Okay, so for example, now if you plug in for the field just rho, you get an estimate for the density of the fluid just based on these particle masses and positions, right? And so you can see that by directly plugging in rho, you're just saying I'm going to smooth over this kernel all of these masses, and that directly gives me an estimate of the density. And the same thing goes for other hydrodynamic quantities. So for example, if you wanted to get the temperature, you'd apply this similar formalism. And so then all that remains is to figure out how to move these particles around, right? And I'm not going to go, before I get to that, one more note about the kernels. So one of the things that is desirable in a kernel is for it to have finite support, so as opposed to a Gaussian, which extends out infinitely, and therefore you would have to collect all of the particles in this sum in order to make an estimate of the density. A kernel that has finite support allows you to just collect a specific number of neighbors, right? And this is actually what makes SPH a computationally feasible method. And so the idea is that, maybe what you want to do is actually keep the number of neighbors constant, and this is typically what SPH codes do. They take somewhere of order 50 neighbors and allow that smoothing length to accommodate that. And so then you can see that if you have a high density region where a lot of particles are packed close together, then you have a small smoothing length and you get this estimate of the density, whereas in low density regions, you're reaching out much further. Okay, so once you've got all of these particles, how do you actually move them around? So this is where you apply just the equation of motion. And I didn't go through the derivation of this equation in the interest of time, but basically you end up with an expression that looks like this. And so you can see that this is then going to be relatively straightforward to integrate. Your smoothing kernel shows up again, and then these variables that are defined for each of the particles, p and rho, et cetera. So up until this point, one of the things that made SPH really nice is that it is an exactly conservative method. Unfortunately, when people started applying it, what they realized is that it doesn't, in this form, do very well with discontinuities like shocks. So if you have a bunch of particles and they move towards each other and interact in a shock, these particles were able to sort of move through the shock. And so that led to the introduction of an additional term, which is called the artificial viscosity. And this is when SPH starts to get complicated. So, I've just parameterized it here as this pi term, but, there are many details and different ways to do this artificial viscosity. There's different switches that you can turn on, because it turns out that as soon as you apply artificial viscosity to take care of shocks, it messes up conservation quantities in things like shear flows. And so this is where I'm not going to get into the details, but most of the modern development of SPH has gone into sort of better ways to deal with that particular problem. So the reason I mention SPH is that it does have a variety of strengths for doing hydro, and in particular, the fact that it has this Lagrangian nature, where the particles, you sort of naturally concentrate particles in regions of higher density and naturally have fewer particles in low density, mean that you can simulate problems that before this method was developed, you really couldn't do. For example, the first cosmological simulations of galaxy formation, where you have huge orders of magnitude difference in density and spatial scale, were enabled by this particular technique. It also, it couples naturally to other particle-based schemes. So, for example, particle-based schemes for solving the dark matter and gravity. And if you wanted to, say, convert mass into star particles, this is a nice way to set up your problem. But there are a number of challenges, right? And so one is that it tends to be more dissipative than grid-based methods. And as I mentioned already, it performs poorly when it's handling shocks and discontinuities. And so people have, come up with a number of ways to sort of fix that, but then those fixes also, generate their own problems. And something that bothers me, even though it doesn't bother a lot of people, is that there's actually no clear way to do a convergence study for an SPH-based problem. You can increase the number of particles, but that is not the same as doing a formal convergence analysis. And so for a lot of problems, what we'd like to know is, are we converging to some actual solution? And it's difficult to do that kind of study with this particular method. Yeah. Right, exactly. So that's the problem, is that it's not directly the same thing as increasing the resolution. Yeah, so essentially that's what happens, right? If you double the number of particles, you increase the mass resolution, which is equivalent to decreasing the mass of the particle. And so you do end up with higher sort of effective spatial resolution in high density regions, right? Because the more particles, you can allow that smoothing length to go smaller. But this is not the same as a formal convergence study where you're increasing the resolution everywhere. And in fact, that's one of the reasons that it's really hard to tell what the spatial resolution of an SPH calculation even is. Whereas, if you run a grid-based calculation, you can state explicitly what your spatial resolution is. When you run an SPH calculation, people will tend to say something like the minimum smoothing length is X, but that tells you nothing about what the resolution is in regions outside of your highest density regions. So yeah, it just makes it a little bit more complicated to compare.
Just out of curiosity, could you not just lay down a virtual read from your SPH, redefine kind of an associate read-based kind of calculation tool, and then try to measure there?
I'm not sure I totally understand what you mean. So interpolate the particle positions onto a grid, and then calculate this quantity. You could, yes, sure, but then you can't. I mean, unless you're talking about doing that at every point in time, which is something that people do, yes. So this is some of the more recent techniques that people are using involve basically that idea, to sort of follow the flow, but then apply a mesh, and in many cases actually then go through the same techniques that they have traditionally used for finite volume methods like Riemann solves and that sort of thing. Yeah. Okay. Okay, so I'm gonna leave SPH behind for the rest of the lecture, and let's talk about, before I get into the sort of details of finite volume, I want to talk a little bit about sort of numerical integration at a more basic level. And so if this is, if you took a numerical PDE class, this will all be review for you. But I didn't have one of those before grad school, so I thought I should cover the basics just in case. So as I said, these equations of hydrodynamics are a set of coupled partial differential equations. And if we discretize all but one independent variable, which is typically time, then we can approximate these PDEs by ODEs, ordinary differential equations. And we have lots of ways to numerically integrate ODEs. So I wanted to start with just a really simple example because it has a nice analytic solution, and so I can illustrate some of these principles. So let's consider, for example, the decay of nickel-56, right? Nickel-56 is a radioactive element. It has some half-life that is here parameterized as tau. And so we can write down this equation. This is an ODE that describes the decay of nickel-56 with time, where we just have some fraction of nickel-56, that's F. And what we know here, right, is we know how that is decreasing as a function of time. Unlike the equations we're going to talk about later, we can come up with an analytic closed form solution for this. So this is something you've all, I'm sure, seen before. So if we integrate, you get log of F equals to negative T over tau plus some constant. We can then exponentiate that, and you end up with the fraction of nickel-56 as a function of time is the constant times exponent minus T over tau. Okay. So something that you also probably already know is that in order to finish this solution, you have to have some sort of boundary condition, right? That's how we know what the constant is. We have to know how much nickel 56 we started with. And in this case, we can just apply an initial value condition, which is just, okay, at time 0, the fraction of nickel 56 is 1, and now we have our solution. Okay, but this is a more general point about, solving ODEs, is that you have to have appropriately defined boundary and initial conditions. And in fact, in solving, some of the problems that we want to solve in astrophysics, it is non-trivial to describe those. Okay, so now we're going to get to the concept of finite differences, and there's a number of ways that we could get here, but I'm going to take us through it in the context of a Taylor expansion. So let's consider some function, f of a, and we're going to Taylor expand around the value a naught. So we have f of a naught plus h is equal to f of a naught plus the first derivative of f at a naught over 1 factorial times h, et cetera, et cetera. Okay. So then I'm going to drop everything after the first order term. So that gives me the second line. If I then rearrange everything, divide through by h and solve for f prime of a naught and drop all of the higher order terms, I end up with this expression. The derivative of f at a naught is approximately equal to just the function value at a naught plus h minus the function value at a naught over h. This is the fundamental finite difference approximation for a derivative, right? And we call it that because it's exactly a difference between the function at these two separate values. Okay, and this is going to form the basis of essentially all of our explicit, forward time methods for integrating the equations of hydrodynamics. So let me put some, perhaps more suggestive variables into this approximation. So if I make that f prime of t, and then I say that, I have t at point I plus t at point I plus 1, and then, over some delta t, you can imagine that this is going to be the time step in our numerical integration. You can see that I have some choices about what values to put in for t on the left side of this equation. And depending on what I choose, we end up with different ways of solving these expressions. So if I pick the value of t at time I for the derivative, then we call this a forward difference. And we call it that because you can explicitly march the solution forward in time in that case. If we use the value of t at ti plus 1, so essentially choose the value of the derivative at the next time, then this is referred to as an implicit method because we can no longer explicitly solve for f of ti plus 1. We need to know something about the derivative at that next time. Okay, so we call this a backward difference. And, we could pick, for example, some centered time, ti plus 1 plus ti over 2, and we would call that a central difference. Yeah. Oh, yeah. Sorry. Sorry about that. Yeah, exactly. Okay. Yeah, sorry. Did everybody catch that? It's supposed to be f of ti plus 1. I've got an extra ti sitting in there. Okay, so let's take a look for a moment at the forward difference version of this expression. So as I said, this is what we would call an explicit method. In particular, we call this the forward Euler method. And if we then solve for f of ti plus 1, had I had the correct equation on the previous slide, then we would have gotten this expression, right? F of ti plus delta t f prime of ti, right? And so you can see that we have all of the information on the right-hand side that we would then need to solve for the value of this function at any point later in time. On the contrary, if we put in the backward difference, then we have this implicit method. Sometimes we can solve in an implicit method. And something that's nice about this particular version is that there's no stability criterion. So unlike forward differences, where there's always some delta t beyond which this solution is not stable, implicit methods are always stable. It's just that they're not always easy to solve. Okay, so another thing to note is that different choices for what we put into that approximation lead to different orders of error in our numerical approximation. And so it turns out that the backward difference and forward difference approximations both have errors that are of order delta t squared. I haven't done the derivation here, but you can work that out. And so both of those, we would say, lead to first order methods. The central difference approximation, on the other hand, has errors that are of order delta t cubed, and so you can often use a central difference if you want to define a second order accurate method. And often in numerical hydrodynamics, we prefer, at least second order methods, especially in time. Okay, so let's return to the example with nickel 56 just to illustrate this a little bit more clearly. What our forward Euler update now gives us for this particular equation is that f of t plus delta t is just equal to f at t plus delta t over tau minus delta t over tau times f nickel 56. And if we plot out that solution, right, so here in black, I'm just showing the analytic solution that we worked out on the first slide. And then the different colors here are the solution for progressively smaller delta t's. And on the right is just the exact value minus that solution. And what you find is, because this is a first order method, that every time you have that time step, your method improves by a factor of 2. And so this is, you can see that we're converging on the correct solution, but we're not converging particularly fast. And so the advantage of higher order methods is that you converge more rapidly to the correct solution. Okay, so speaking of higher order methods, I mentioned that if we used the central difference, we could come up with a second order method. But what you'll find if you plug in the central difference to our finite difference approximation is that then our value, f of I plus 1, depends on the derivative at the half time step. And we don't know the derivative at the half time step, so what are we going to do? Well, we're going to just use the forward Euler method to get an approximation for the derivative at the half time step, right? So that's what this bottom line is showing. Now we have some approximation for y prime of t at h over 2. So h here you can think of as the time step. Once we've got that, right, then we can just use that in our full update centered difference formula to get this expression. And so this is, this particular expression has a variety of names. It's called the midpoint method or the modified Euler approximation. It's also the simplest example of what we call a Runge-Kutta method. And so Runge-Kutta, you can create this, use this same strategy to create progressively higher order approximations. And in fact, one of the most common ODE solvers is a fourth order Runge-Kutta method. And you can use those methods as the basis for numerical hydrodynamics integration. We also sometimes call this a predictor corrector method, and you can see that's because the first thing we do is sort of predict the value using a low order method, and then we correct it using these higher order terms. So just to sort of explicitly show, what would these different methods give you if you're approximating, this function 1 minus x cubed. You can see backward Euler, you're sort of always going to undershoot the solution, but the smaller the time step or the spatial step that you take, the better you'll do. Forward Euler, you have the opposite problem, whereas midpoint, you're actually taking this combination of slopes in order to get to a more accurate estimate. And so this is just, again, showing that these higher order methods converge to the correct solution more quickly, which is why they're desirable. You might be wondering at this point, why don't we always just use the highest order method? And the answer, of course, is that they're computationally much more expensive and get progressively more so as they get more complicated. Okay, so briefly then, finite difference methods are just ways that we can solve ordinary differential equations or partial differential equations by approximating these derivatives as finite differences. And so, you can think of this as just having some arbitrary function where we've defined that function at a series of points, and then we're going to define the derivatives by taking differences between those points. And that allows us to convert these equations into systems that can be solved numerically. So as our first example, we're going to return to the advection equation, which you've already seen several times. So here I'm expressing it as du dt plus a times du dx equals 0. And so if we return now to our first order forward time method, we can create a finite difference approximation for that time derivative. So then we have du dt is equal to u at tn plus 1 minus u at tn over delta t. Solve that, and we get a value for u at tn plus 1, but we still have this partial derivative in x to deal with. So what are we going to do about that? So it turns out, it's usually easier to deal with the spatial derivatives, because if we've got a well-posed problem with initial conditions, then we know a lot about what's going on in space near these points. And so, for example, in this case, we could use what's called a forward space approximation, where we're going to use the value of I plus 1 to calculate that dx term. We could use a backward space approximation, where we're using the value at x of I, or a central space approximation, where we use both. And this is just for reference. We often express these methods in terms of their space-time stencil. And so in this case, right, this would be a forward time, forward space stencil, where this is always the spatial direction, this is the time direction. So here it would be saying, all right, in order to estimate the slope, I'm going to take one element forward in space. This is forward time, backward space, forward time, centered space. Right? And so one of the reasons these stencil diagrams are useful is that it gives you some idea. For these spatial approximations, you could go out to many surrounding points to get progressively higher order approximations for these derivatives, and that gets progressively computationally more expensive because you need to keep more data. If we had actually used, for example, if we considered our advection equation, where we had a wave that was traveling to the right in the problem, right? If we used forward time, forward space in order to calculate the derivative, what we would find is that we have a violently unstable solution, right? Because it knows absolutely nothing about the derivative and the direction of the speed of flow. On the other hand, if we had used forward time, backward space, we would have found a relatively diffusive but reasonably traveling wave. And so this highlights one of the main features that we want to take advantage of in solving these numerical problems, is that it's often you can use a not necessarily a high order method if you know something about the physics of the problem. And so in the case of advection, right, we can use forward time, forward space, or forward time, backward space, depending on the actual direction of travel of the wave. And so that's essentially what this says, is this is just now our finite difference approximation for the advection equation, but taking into account that we understand something about the physics of the system. Okay, so one other note. I think most of you said that you already are familiar with the CFL condition, but just in case, it's worth mentioning that these explicit schemes are only going to be stable in time if you satisfy this criterion, right? And a sort of formal definition of the CFL criterion is basically just that the the numerical domain of influence has to encompass the sort of physical domain of influence of the problem. But you can think of this for the advection equation as basically you can't take a time step where that wave could have traveled more than one of your distance steps over the course of that time step, because then you'd be missing information in the problem. And so we often have, for finite volume methods, the CFL criterion is often expressed as some function of the sound speed and the grid spacing. And so when we get to sort of Riemann problems at cell interfaces, you can think of it as basically you can't allow waves from separate cell interfaces to interact within a cell over the course of a time step. All right, so now I want to get to this idea of finite volume methods. And so the idea is, in finite difference, we were gonna represent our function as a series of discrete points along some mesh spacing. In finite volume, I'm going to actually express the conserved quantities as integral quantities. So if you think, here is an actual cell in the grid. Within that cell, we can think of having this vector of conserved quantities, and these are just the same quantities that we've been talking about this whole time. We have density, you have 3 components of momentum, you have the total energy. And so then if I, set up an actual grid with x, y, and z directions, I specify that I have some, spatial distance delta x, I can write these conserved quantities as just an integral over this volume, right? And so that's all that this expression says. And the idea in a finite volume method, right, is just that I want to go from these values of u at time t to the values of u at some later time, t plus delta t. And so how are we going to do that? And so the answer is that in addition to having these, volume averaged values of the conserved quantities, we can also have space and time averaged fluxes. And so, if I rewrite this, here fluxes on the x face I'm calling f, on the y face I'm calling g, on the z face I'm calling h, then you can see that I've now rewritten my sort of conserved variable update in terms of the flux at one interface minus the flux at the other interface has to be equal to the change in time of that quantity. So this is just another way of expressing the conservation equations. And just so we're clear, right, these fluxes are averages across the area. So you can see I'm taking, this integral for f, I'm taking across dy dz, but they are also integrals in time. And so in order to integrate across the course of a time step, I need to know what was the flux across that entire time step. And so as I'll get to in just a minute, actually, this is the fundamental trick in developing a finite volume method, is how do you decide what those fluxes should be? How are you going to do that integral in space and time? So just to sort of recap, if I have my vector of conserved quantities, I have my 3 flux vectors, then I can express this just, this is just the same conservation equations that we were expressing before. Okay, so okay, so great. I just said this. So at this point, we haven't actually made any approximations. This is an exact expression, and so all of the the differences between these different finite volume methods are going to come in how we decide to approximate the values for these fluxes. So the first suggestion that was made was by Godunov in 1959. And the idea was that he suggested that you could maybe get appropriate fluxes by just assuming that the average values for these quantities in the cells were piecewise constant, and then solving a Riemann problem at the interface between the cells. And so, this is just, now I'm representing, if I have 3 cells, I'm looking for the fluxes at these interfaces. And it turns out that if we do this, we're going to end up with a first order upwind method. So now I'm going to talk a little bit about the Riemann problem and how we actually solve it. So the idea is that you have some interface, and on the left of the interface you have one set of states, and on the right of the interface you have a different set of states. So returning to the linear advection equation, this is sort of the simplest example of a Riemann problem. Let's say that you have a left state with one value of the speed, and a right state with some other value of the speed, and there's this discontinuous interface. What we find is that this value q is then going to be constant along a characteristic in the xt plane. So I know you saw some of this in the last lecture, but right, it's worth pointing out that this is basically just saying that as long as I know the value at x naught, then if I follow this characteristic, which just has the form x naught plus at, that the values of those variables do not change along that characteristic. And so in the context of the Riemann problem, then, right, you can think of this as saying that as long as I know the speed of this characteristic, then in the xt plane, I can always define where I have the left state variables and where I have the right state variables at any point later in time. So the linear advection equation is fairly simple. It has one variable and it has only this one characteristic. That characteristic is associated with what we call an entropy wave, because the only variable that changes across it is the density. And the velocity and the pressure are going to be equal. If we look now at the 1D version of the Euler equations, then we can follow the same sort of characteristic analysis. So again, I'm going to write them in this sort of flux conserved form, where I have my set of conserved variables, I have my set of fluxes, and the initial conditions, as before, are just UL if I'm on the left side of the boundary, UR if I'm on the right side of the boundary. I can then rewrite this into what's called the quasi-linear form of the Euler equations. And you can see that all I've done here is I've defined this matrix A. A is the Jacobian, which is to say that it is the derivative of the fluxes with respect to U. So I didn't bother writing out the math of this, but you can do this algebra. Basically, you just have to, define U such that you have, the first variable is density, the second variable is momentum, and the third variable is energy, and do your substitutions, and then you actually can come up with this Jacobian. Here I've also just swapped in H, the total specific enthalpy for conciseness. And so what's special about this Jacobian, right, is that it satisfies this relationship. AU is equal to F of U, and we can actually calculate the eigenvalues for it. And so it turns out that those eigenvalues are, lambda naught is equal to U, the flow speed, lambda plus is equal to U plus A, the flow speed plus the sound speed, and lambda minus is equal to U minus A, the flow speed minus the sound speed. And so it's actually this property that A is diagonalizable with real eigenvalues that makes us refer to this system as a hyperbolic system of equations. And what that means is that these certain quantities, which are called invariants, are going to be, transported along characteristics in this plane. Okay. So what does this mean, right? This means that if I then look at the xt diagram for the Riemann problem for the Euler equations, it has these, these three characteristics. And so I can then associate those characteristics with things that we sort of know and understand, in the sense that this central characteristic is just associated with the bulk speed of flow. So this is a contact discontinuity in this diagram where the density changes. The rightmost characteristic is associated with U plus A, the flow plus the sound speed, and the leftmost characteristic is associated with U minus A. And so in the Riemann problem for the Euler equations, right? This is always, you always get this set of 3 characteristics. That doesn't always mean that you have to have 3 waves, but these are the 3 speeds with which information can propagate in the xt plane. And for solving the Riemann problem, it's also useful to then define these as sort of 4 different states, where you have the leftmost state, the rightmost state, and then these states within the star region. And so the reason that we generally call it the star region is that the pressure and velocity are constant in this region, right? It's just the density that has changed. So if we then think about this, right, the idea is that we want to solve this Riemann problem at an interface. We have discontinuous solutions generally. I mean, we have discontinuous states on either side of the interface. And so the actual values of those variables on either side of the interface are going to determine the pattern of characteristics that you see later in time. So for example, if I have a left state with high density and pressure and a right state with low density and pressure, then I'm going to end up with this characteristic diagram. So this is saying that this is actually showing all 3 kinds of waves that you can have. You can have a shock, which is propagating out to the right in this case. You can have this contact discontinuity, which is also propagating to the right. And then you have this expansion fan or rarefaction wave, which is just to say that you have, this leftmost, the head of this fan is moving at u minus a, but then you have this region over which the variables are varying smoothly. Similarly, if I just swap these, then you get the exact opposite solution. If you have, say, 2 converging flows, then you can end up with a state where you have a right-going shock, a left-going shock, and a contact discontinuity. If you have diverging flows, you can end up with basically a single expansion fan and a contact. So just as an example of what the solution to a Riemann problem actually looks like, this is the sort of classic case. So Riemann problems are often associated with shock tubes because a shock tube is actually just the setup for a Riemann problem where you have a state on one side, a state at the other side, some thin membrane in between them, and then you burst that membrane at 0 time, and you can actually watch in physical space the solution to these problems. You can't make every Riemann problem in a shock tube because it turns out it's really difficult, for example, to get different velocities. But you can definitely do this particular case. So this is what's called the SOD shock tube. You have high pressure and density on the left, low pressure and density on the right, no bulk motion for either side. And so then if I actually just play this, this is showing you the evolution of the exact solution to this Riemann problem in time. And what I want to point out is that this is a self-similar evolution in time, right? And that's just another way of saying that those characteristics in the xt plane are in fact moving in straight lines. And so if I replay this, you can see that it's just exactly that. You have these 3 waves that are moving out at this constant rate in time. Okay, so I'm spending a lot of time on Riemann solvers because Riemann solvers are this sort of fundamental unit in finite volume codes, and one of the reasons that they've been studied so much is because it turns out that to do that, to exactly solve the Riemann problem, is possible in the sense that you can write out, if you use the shock jump conditions and you do a bunch of algebra, you can write out exactly what the solution is for every variable that you care about in each of these 4 states. Except what you'll find is that to get the pressure in this star region, you have to do an implicit solve. And so this is certainly something you can do. You can do a Newton and Raphson iteration. You can usually converge relatively quickly. The problem is that, if you are doing this in a code where you have millions or billions of cells, and that's millions or billions of interfaces, and then you have to do a Riemann problem for every direction, and if you want to do a second order in time method, now you're up to 2 Riemann problems for every direction, that this can get very expensive, computationally speaking. And so a lot of work has gone into finding essentially less computationally expensive ways of solving the Riemann problem. And so one example is that rather than solving this exact expression for the Euler equations, you could calculate a numerically exact solution to a linearized version of the Euler equations. So here, instead of the full Jacobian, this is just some matrix where I've defined some sort of average state between the left and right. And so, for example, if you've heard of Rowe's Riemann solver, it's probably the most famous of the linearized Riemann solvers. And the point is just that they allow you to do this all through matrix operations with no implicit solve. There are sort of various levels of accuracy that you can get in an approximate Riemann solver that have to do with how many of these waves do you take into account. So there are very simple Riemann solvers that ignore, for example, the contact discontinuity. As you can imagine, then those are very diffusive with that sort of discontinuity in real space. Just one more note since I'm on this. So I'm not actually going to mention it in this talk, but my personal area of expertise is putting, all of these numerics, solving them on GPUs, graphics processing units, instead of CPUs. And some of what I'm saying goes out the window when you do that, because this is, a technology that has really different limitations than CPU computing. And so, for example, doing an exact solution to a Riemann solve doesn't add very much computational expense on a GPU as compared to a CPU. So some of these things are, sort of a matter of tradition, whereas now there's, you have more options. Okay. So a quick note about diffusion. So let's take, for example, the simplest approximate Riemann solver that you can come up with. So this is the Lax-Friedrichs flux function. So the idea here is this is shorthand for the flux for the Riemann problem as a function of UL and UR. Basically, you just take the flux from the left state, where those flux functions, right, were given by rho u plus p, etc., and the flux from the right state, average those two, and then subtract off this term that has to do with the maximum signal speed, where that's the u plus a terms as a function of the right and the left states. And so it turns out that, in this particular Riemann solver, and so you can see why this would be very fast, right? Basically, you just calculate all of these variables, immediately select your signal speed, and you're done. And so if you care a lot about the number of operations that you're performing, this is good. The first term on this side is just a second order accurate estimate of the flux. But it turns out that if you just used that, right, this would be an unstable method for the same reason that centered difference approximation to the advection equation was an unstable method. You have no information about the actual physics of the solution. And so that's what this second term incorporates. It's the upwinding term, but it also is effectively a numerical viscosity, right? And so you can actually calculate the level of numerical viscosity. In this case, it just goes as S max times the grid spacing over 2, where this is, as I said, just this maximum signal speed. So it's either UL plus A or UR plus A. And so in many cases, you actually need some numerical viscosity in order to stabilize your scheme. So people will often report that their scheme is great because it has absolutely no viscosity, but that's not necessarily a good thing, because because you often need some form of numerical viscosity to stabilize the scheme. And the reason is that we've been solving all of these sort of ideal equations, but we're leaving out actual physics. So things like viscosity and conduction that smooth out some of these features. And so if we have no numerical way of taking that into account, then we'll find that the solutions that we get are actually unstable. Okay, so just to review, we call something a Goodenough method if we have this just first order expression. That's not first order, it depends on the fluxes, but we have this explicit expression for the update of the conserved variables that depends on these fluxes. And in the original Goodenough method, those fluxes are just taken to be the solution of a Riemann problem where we assume that all of the values of the cell variables are piecewise constant. Okay, so as I said, this is a first order method, both in space and in time. As a result, even though it was a large step forward at the time, it's not actually that practical because it's very diffusive. So, the idea then is that what we'd like to do is take this general framework of solving Riemann problems at interfaces and discretizing time and space derivatives, but we'd like to improve it by increasing the order of accuracy of the approximation. And that's basically where all of the work has gone in the 50 years since. So for example, the first second order Goodenough method, which was called muscle, was developed by Bram van Leer, and the idea there was just, okay, do the same thing, but a higher order spatial derivative. So take piecewise linear reconstruction within the cells. And so you can do this for progressively higher orders in space. So, piecewise constant method versus piecewise linear method versus piecewise parabolic method. Something to note, right? It does generally result in a more accurate computational method, although I should note that this is only for regions of smooth flow. So at discontinuities like shocks, all of these methods revert to first order, and you need them to, otherwise you develop these violent unphysical oscillations. But also, as you do this, it gets progressively more and more expensive. So for example, for a piecewise parabolic spatial reconstruction, you now need information about two cells on either side of the interface. And you can imagine then if you are dealing, for example, with boundaries of volumes, that this sets the number of ghost cells that you have to carry around. So in addition to the fact that the actual calculation of the spatial derivatives is more expensive because you're doing more math, you also have to carry around more data in your stencil, and that tends to make the method more expensive. So it's not a good idea necessarily to just go to some fifth order spatial reconstruction method. It may actually be more computationally worthwhile to just increase the number of cells or decrease the mesh spacing. Okay. Yeah, so it really depends. I would say, the majority of finite volume calculations that have been done in the last 20 years use piecewise linear. Some use piecewise parabolic. So there's actually the piecewise parabolic method as originally formulated was in the mid-'80s by Colella and Woodward. And that's a pretty popular method. And so it probably depends a little bit on the subfield. But for example, in like cosmological simulations that have been done with like AMR, because only recently have people started to use PPM. Yeah, so there are other methods that I'm not going to talk about called like weighted, essentially non-oscillatory methods that are basically higher order spatial discretizations, but they're finite difference methods, and so it sort of depends a little bit on the problem. Yeah. How do you choose a slope? All right, I'm going to talk about that in just a second. Perfect. Okay, so what else did I want to say about this? If you increase the order of the reconstruction, right, yeah, this is an important point that I think is not always obvious. The first time I gave a talk on this, and I showed ppm and I showed this kind of diagram, someone said, okay, but then why do you have to do a Riemann problem, right? There's no discontinuity at the interface. So one of the things that happens is if you go from piecewise constant to, say, a piecewise linear reconstruction, what that means is that you can imagine this fluid as actually moving, right, in space. So if I think of going to the half time step, say, where I want to estimate these fluxes, right, because I want my flux calculation to be an integral across the full time step, then this fluid now has actually changed its properties over the course of that half time step. And so essentially what that means is that if you do a higher order spatial reconstruction, you also need to have some way of propagating that information forward in time. And so this is why if you do a higher order spatial approximation, you are always also going to want to do, say, a second order time approximation where you do something like use first order fluxes to predict the interface values at the half time step, then do this spatial reconstruction and another set of Riemann problems, and then update. Okay, so the slopes. How do we actually calculate the slopes? So you can imagine, right, we've talked about finite differences, we've talked about how there are all of these different ways that you could choose to interpolate. The simplest, right, of this would be like a forward difference method, is just if I want to calculate the slope here, then I'm just going to take, I and I minus 1, and that gives me some slope for this interface. If I want the interface here, I'm going to take I plus 1 and I. This is called the Lax-Wendroff slope. You can probably immediately see that this is going to be a problem because, if, for example, the fluid is moving in this direction, now I've basically overshot what the actual value at the interface should be in this case. And so this is sort of an extreme example, but in general, if you are applying piecewise linear methods to calculate slopes and you have something like a local maximum or even a very steep gradient, you can tend to overshoot the actual values of the cell averages, and that leads to oscillations in your solution, which you don't want. And so there's this whole class of methodologies that are devoted to trying to sort of figure out how to reduce those oscillations, because we want higher order methods to improve the accuracy, but we don't want additional oscillatory behavior. So this is the concept of basically total variation. So you just want to know whether or not your solution is becoming more or less oscillatory in time. So you just take the solution at time I minus the solution at time I minus 1, absolute value, and sum over your elements, and that gives you the total variation. A method is said to be total variation diminishing, so if you've heard of TBD methods, if that value decreases with time. Okay. And so the way that in practice people do this is by applying some form of a slope limiter. And there are lots of different forms of slope limiters. In fact, in the practical session later, you're going to get to play with some code that allows you to try out lots of different forms of slope limiters. One of the most common, for example, is the min-mod limiter. The idea there is if I was looking at the interface between those two cells, I could imagine taking the slope from the right-hand side, basically, or the slope from the cells on the left-hand side, and just applying whichever of those is smaller. Or if I have a local maximum, so this is saying, this is the ui minus 1 over delta x is A, ui plus 1 minus ui delta x is B. This just says, whichever is smaller of A or B, or if the product of A and B is less than 0, then I have a local max or a local minimum, then just take that slope to be 0. And in practice, right, maybe that looks something like this. If the Lax-Wendroff slope was this solid line, then min-mod is this sort of more shallower slope line. This is good in the sense that it's going to reduce oscillations in the flow, but you can also imagine if you actually have a function that has a lot of local maxima and minima, so some really oscillatory behavior, and you don't have enough grid points, that slope limiting is also going to cause you to essentially diffuse away those maxima and minima. And similarly, if you have something with a very sharp discontinuity, like a square wave, slope limiting is going to cause you to sort of gradually lose the sharpness of those edges. So there's always a trade-off when you're using a slope limiter between, adding additional diffusivity in order to damp down those oscillations that you don't want, and losing sharp features of the simulation that maybe you do want. And so it's just, in practice, people usually, I think, just sort of pick their favorite one and go, but it's something to keep in mind. Okay, so far, I have only been talking about the hydro equations without source terms, and that there's plenty more to say on that, but I thought I should at least mention how we couple some source terms, and you're gonna get more detail, I think, on some of these things later in the week. But for some stuff that I think maybe won't be covered. So for example, some of the common source terms that we have to deal with in astrophysics, these include gravity, heating and cooling terms, conduction and viscosity, chemical reactions, in some senses, centrifugal terms can be expressed as source terms. So there's lots of versions of these. And essentially all I mean by a source term in this formalism is something that shows up on the right-hand side of one of these conservation equations. So if this is my, my expression for flux conservation, then I have some source term. It can be a term in any one of the equations, right? So an example, right, might be radiative heating and cooling terms, that this is just going to show up on the right-hand side in the energy equation. If I have some, heating source term, maybe it's photoelectric heating, and then some cooling source term just due to optically thin radiative cooling of the gas. So the question then is, what do we do with these terms that we haven't taken into account at all in our solution to the hydro equations yet? And it depends a little bit on the nature of the source term itself. So basically, I think the most common approach still is something called operator splitting. So the idea there is that you just go through your hydrodynamic update first. So do everything we just said in order to get from the adiabatic version of the hydro variables at time n to your updated version at time n+1, but you haven't taken into account anything about the source terms. And then just apply the source terms as formulated at time n. Okay, and this is, by nature, it's a first order approach because we're just doing delta t times s. So actually, let me just say, this works fine as long as the time scale over which those source terms are varying is long relative to the time scale over which the adiabatic variables are changing. So basically, if you're considering, for example, cooling of the gas, if the cooling time is long relative to the actual adiabatic time step that you've taken in your hydro integrator, this will work fine. It's not a problem. It's basically just a small perturbation on those equations. However, the time scale that's associated with those source terms could also be very fast. And in that case, we refer to those source terms as stiff, and then you will generally run into problems if you just follow an operator splitting approach. So in that case, right, another option might be to do an implicit method. And so often, for example, if you're dealing with chemistry, this is something that people do, is apply an implicit method for the source terms on top of this explicit update. And this is just a super short version of this. If you get into like radiation hydrodynamics, etc., it gets much more complicated. Okay, so to summarize, As we've demonstrated, the Euler equations are this set of coupled hyperbolic partial differential equations, which means that generally speaking, we're going to want to solve them numerically. There's a couple of common techniques that we use in astrophysics to do this, primarily particle-based techniques, including SPH, and grid-based techniques, so finite difference and finite volume. And you can vary the levels of complexity for all of these techniques. And so essentially, what this all boils down to is that the details of the numerical algorithms that you choose are going to determine things about the solution that you get. And different levels of accuracy are going to be required for different solutions. And so you should think carefully about which algorithms you choose before you actually solve your problem. Some algorithms are going to be better suited to some problems than others. Oh, okay. I guess that's it. I know I'm a little short on time, but I was kind of expecting more questions. So, yeah. Is there anything? Yeah, I can answer questions if you guys have stuff you wanted to know more about.
Showed this slide earlier where the gradients were second order.
Mm-hmm.
Where you didn't have that discontinuity between cells.
Sure.
So I was wondering if you do that, are there times when you can actually lose mass or density or any of the high-dimensional quantities? Is there or are they by default conserved? The gradients.
So no. So you don't lose the conservative properties. Were you talking about like this situation? Yeah. No. Because the finite volume methodology assumes conservation, if I don't apply any source terms, then no matter what I choose for the fluxes, right, whether I calculated them using a constant method or a higher order reconstruction method, whether I evolved them forward in time or not, you can never lose mass or momentum or energy. That's basically the definition of a conservative method. And the reason, right, is that I've expressed the update. Where did it go? Let me find, okay, this will work. I've expressed the update like this. And so if you think about how does this actually get applied on a grid, it means that any flux of mass, say, that goes into one cell has to have just left the next cell. And the same is true for momentum, and the same is true for energy. So this is why people like conservative methods like this, is because at face value, if you don't incorporate any source terms, there's no way you can lose any of those quantities, because they all are transported by fluxes between the cell interfaces. Yeah.
To add something slash ask, you can, of course, interpolate on different quantities. You might interpolate on primitive quantities or the conserved ones, and if you're interpreting on conserved quantities, you might choose an interpolant which preserves the cell mass, the mass in that cell. And,
sure.
So, as you said, no matter what, you'll still, by construction,
preserve
the integral of mass and energy, regardless of the interpolant you choose. But do you find that you have different stability properties?
Absolutely. Yeah. So that's something I didn't really talk about very much. But when you're doing that, back to the linear, when you're doing the various forms of like spatial interpolation, you can choose different sets of variables to do that on. You could do it with the conserved quantities, mass and momentum and energy. You could also do it with the primitive quantities, which are density and velocity and pressure. You could also, and in fact, I think this is a really nice way to do it. You could do it with the characteristic quantities, which don't have there's not a straightforward way to express them, but they are literally those characteristics that are preserved in the Riemann problem. And so choosing different sets of physical variables to interpolate on can increase the accuracy of the flux calculation. In some cases lead to, for example, less oscillatory behavior, et cetera, et cetera. But it's never going to change the fact that these quantities are conserved, because it's all just about what did you choose to put into the left and right states for your Riemann problem, and then you get a flux out that has to be the same as the flux, the cell before and after. Yeah. Okay. Good. Sure. Yeah. Yeah, so I didn't actually write down the analytics for that, but basically, I mean, so you just start with the equation of motion, and so you have, you know, your velocity field that's this convolution with the kernel, and you have your grad p, and if you do some algebra that allows you to, you know, move that derivative around, then you'll end up with these velocity differences that get you to, you know, the pressure differences between. Yeah, I mean, if I don't know, it's not worth going all the way back, but there was a you know, a pressure difference basically in that expression for yeah. Well, that's because you have that rho over m in the definition of the smoothed field. Yeah, so it's just algebra, as I don't know. Yeah, I don't have it written out, so I can't do it for you. But it's just using you know, algebraic and substitutions for the derivatives, et cetera. You can get to exactly that equation. Yeah. Yeah. Yeah, so that's why I was talking like when I said predictor corrector schemes, that's like a second order or can be a second order time scheme. You can what? Yeah, so basically there's two separate orders, right? There's the order in time and there's the order in space, and those don't have to be the same. And in general, right, if you have a smooth flow, like you're just propagating a sound wave, for example, if you have a method that is first order in time and first order in space, then you'll see, you know, the L1 error decrease linearly. If you have a method that's second order in time and second order in space, you'll see the L1 error decrease quadratically, et cetera. But, you know, this is why I was sort of trying to distinguish between the order in time, which comes from how you discretized the time variable. That could be a second order scheme. It could be a fourth order scheme. I mean, people do fourth order Runge-Kutta for the time. That's totally separate from the order in space. And the order in space, right, is only applicable in smooth regions of the flow. So if you have a shock, it's always going to be first order in space. Yeah. Right, so in practice, like I said, I think the most common is still second order. So second order in time, second order in space. But it's becoming more common for people to choose third order spatial methods, like PPM is popular. And in specific fields, again, because it depends on the problem that you're trying to solve, right? If you're trying to solve a problem that mostly consists of smooth flow, it can totally be worth it to go up to much higher spatial order. In astrophysics, because we're often dealing with shocks, it's usually not worth it to go to higher spatial order because you're gonna throw all of that out if you're at a discontinuity anyway. Yeah.
So for Riemann problem, you're dealing with the boundary between the two neighboring cells.
Right.
But presumably, in real numerical experiments, the states within the cells are actually pretty similar to each other, right? So the shocks and the discontinuities that you are dealing with are quite weak.
Well, so not necessarily, right? And that gets back to what I was saying about the interpolation, the spatial interpolation. So, I mean, you can see why in piecewise constant, they're not necessarily very similar. In piecewise linear, sure, you could assume that they were going to be similar, except that this is just the spatial discretization. But like I was saying, this is, you want to use the values of the fluid at the interface halfway through the time step if you're doing a second order time method. And that means that this, you know, if you just think about the density and assume that these are all traveling with speed u, then this interpolation has now moved over here, and this one's moved over here, and so you can actually end up with much larger differences at the interface once you do that propagation forward in time. So this is also done, for example, in ppm, it's done via the characteristics. And basically, you take some estimate of the actual, density field, say, you reconstruct it at third order, but then you calculate all of the characteristics for that field, and you estimate which of them will have actually propagated to the interface by halfway through the time step, add up all of those contributions, and that's the state that goes into your Riemann problem. So you can easily have, like discontinuities even in a region that has relatively, smooth flow in the actual solution. Good. We'll leave it there, and then yeah, we can go through the practical in a little bit and address any more questions.